He didn't want to be there. He cuddled for a while and then he ran away. I'm calling this part 3. I'm taking a radical departure from our previous naming scheme. So this is part 3 because once they're up on YouTube, they will have no concept of days or time. And so we're naming them after the stream index, not the days. Okay. All right. Let's see. Are y'all here? I need to ping students. There we go. Please react to that message if you are present. Neat. Okay. All right. What's happening? I should open my notes. There we go. Okay, I think we're ready. I just need to arrange some windows. There we go. Something like that. That. Are we going to talk about the funny cross product? Soon. We have one more thing. One thing in between us and the cross product. Just arranging all of my windows because it's getting a little messy. Okay. All right. Okay. Where's my tablet pen? There it is. Oh, actually need to get some water. I'm sorry. I need water. Oh shit, I forgot about the cat ears. That was a real close call. Oh my god, I wouldn't have been able to do math if I forgot about those. Okay. Okay. All right. All of my meandering now before I start in YouTube, that's going to show up as a comment in chat where someone is like, lecture starts here. That's what I've caused now with all of this. Okay, so we've been talking about doing this type of transformation where we have something in one space and then we transform it to another space or between coordinate systems. And generally in games, you almost never do it this way. If you want to do like a full transformation from one coordinate system to another, you generally use something a little bit more advanced than just these elementary methods that we were using here. And that is to use something called transformation matrices. And I'm sure you might remember matrices from school. I never had them in school, but some people do. So matrices. So matrices is just a different way of storing numbers in math. Like we have our vectors where we have some, you know, x, y, z values, and we sometimes write them like this, right? And so this is kind of a container for 3 numbers, right? But there are other containers, we can write them in different ways. So sometimes you write things in an object called a matrix. So usually you have these brackets like this. So this is a matrix, and maybe we can store a vector in a matrix. So we're going to have our x, y, and z components. We can write them as a column matrix like this. And so this is called, if you write a vector in this format, this is called a column vector. And it is a column matrix because it has 1 column and then 3 rows, right? But you can make matrices that have any number of columns and rows. So you can have a matrix that, you can have a 2 by 2 matrix and maybe have some values in there. Maybe you have 0, 1, 2, and 3. So this is also a matrix. So this is 4 numbers that we're storing in this matrix. And so again, matrices are just a way to store numbers and manipulate them. Now, there are a lot of rules about how we multiply matrices together. So matrix multiplication is a special type of multiplication that is quite different from just multiplying numbers directly. But in games, we generally mostly deal with a specific type of matrix. So there's a type of matrix that will encapsulate and do this type of transformation that we're doing up here. And so we're going to talk about transformation matrices. Aren't matrices quite similar to arrays? Basically, yeah. You can store matrices in an array, like in your code if you want to. So yeah, they're very similar. One thing that is a little bit different is that if you have a matrix like this, this is not the same thing as a row matrix. So if this is your matrix, these are not equivalent. But if they're arrays, you would kind of consider them to be the same thing because arrays don't have an orientation, right? But so this is a column matrix and this is a row matrix. Just one thing to keep in mind if you're making that comparison. All right. Maybe we'll keep that just as a little souvenir, just so we don't lose that. I'm gonna scoot it over there. Okay. And so there's lots of multiplication rules for how you multiply matrices and how they interact with each other and whatnot. If you are, so for example, if you have a row matrix, isn't that the same? Yes, but that's a 2-dimensional array. So yes, in that case, it would be the same. But they still have special multiplication rules. So it's a little bit misleading to call them arrays, but you can certainly store them in arrays. But let's say you have a vector. So usually we have a vector that we just name A, right? So we have A, And then maybe we want to do the dot product with B. So this is how you would write the dot product generally, right? So A dot B. But we can actually write the dot product in matrix form. And so if we write the A vector, we can do AX as the first element in the matrix, and then A Y, and then A Z. Sorry, my handwriting is awful. So this is a row matrix. We can multiply that by a column matrix that contains multiplication. You just omit the symbol. You don't write anything in between. And so then this would be a column matrix using B. So B, BX, BY, and BZ. So if you multiply these two matrices, this is actually the same thing as the dot product. Because of the multiplication rules in how matrices multiply together, these actually result in a single value that is equivalent to the dot product. So this is the same thing. We're not going to go too far into exactly how you do matrix multiplication, mostly because it actually doesn't really matter. But one way you can sort of think about it is that if you take this whole column vector, it's kind of like you're taking it and rotating it and placing it on top, and then you're multiplying this by this, and this by this, and this by this, and then adding them all up. Which is exactly what the dot product does, right? There are many ways you can visualize that. There's a kind of nice visualization thing. I think it's this website. Yeah, so if you want to multiply these matrices together, let's reduce that a little bit. So if you multiply them, it's kind of like you're taking all of the elements and like multiplying each element and then summing them up. So it's kind of like each thing is a dot product with every row. So it's going to do a dot product with all of them, and then you end up with the final matrix. So if you want this website, if you just want to play around with matrices, there you go. In either case, this is very useful, especially when dealing with transformations. Because, let's move that aside. There's a very, very, very useful type of matrix we can use called the transformation matrix. So if you, let's first imagine a coordinate space. So we have some axes, right? Here's our. This is 3D now. We're jumping into 3D. So if you have some transform in Unity, that transform has a position, right? And so there's a position vector from the origin to where your transform is, right? But then you also have the basis vectors. So you have the x-axis, and then you have the y-axis, and then you have the z-axis if we're in 3D. So this one is pointing away from us. Imagine that it does. So this is this fully describes the position and orientation of the transform, right? But usually you don't actually store this in these 3 or 4 separate vectors. Like you don't actually generally have like a position vector, a right vector, a forward vector, and an up vector. Quite often you store all of that in a matrix. And usually you would store that in a 4x4 matrix. Sometimes you would store it in a 3x4 matrix, but the 4x4 is a little bit more general. Okay, so we're going to talk about the matrix 4x4. This is also a data type in Unity, so you can use this type in Unity and do stuff with it. And so, why not 3 by 3? We'll get to that in a moment. So in a 4 by 4 matrix, so that means we have 16 elements. I don't know how to count. Might have to change the size of this. So if we have a matrix, we can actually store this information in that matrix. And so the way that this is generally stored is if you take the x-axis, you can store the x-axis as a column vector in the first column of the matrix. So you would, because every vector has 3 components, right? Every vector has an x, y, and z component. And so the x direction here, this vector, is stored here. And so we have x, the x component of the x direction, and then we have the y component, and then the z component. And at the end, we usually have 0. Gonna talk about that later. So we're actually storing the direction, like this vector, we can store that as a column here. And then we do the same thing for the other vectors. So we have the up vector here, the y direction. We can store that as well. So the x component of the y vector, the y component, and the z component, and then 0. Then we do the same thing. The z direction, that's this vector right here. So the x component of the z vector, the y component, and the z component, and 0. Okay. And then, so now we've stored the entire information about the orientation of this object in this part of the matrix. It is actually possible to kind of cut this off. So we can, if we do this, then this is a 3 by 3 matrix, right? If you have orthonormal vectors like this, as in they are orthogonal to each other and they are normalized, then this is actually a rotation matrix. You can use this matrix to rotate objects. And so if we multiply this by a vector, like any vector, in this case a column vector, you know, that vector in and of itself has its own components. If we multiply these together, we will get another vector that is this vector rotated by this space or this rotation. So this is actually transforming from a world space direction and then rotates it with the orientation of this object. And so this is often called a rotation matrix because that's what it does. What does orthogonal mean? Orthogonal means that it's kind of like perpendicular, right? So these two lines are parallel and these two lines are orthogonal, right? Okay, so what this does is that it will take this vector and then effectively it rotates it from this space. And so this has an orientation, right? Like this fully describes the orientation of your transform, and that then transforms it to our new vector, but transformed using this rotation. And so that's one part of the matrix 4x4, but this is just a 3x3 matrix, right? So we're missing a few things. But you can use 3x3 matrices to do 3D rotations. And this is used a lot for many different types of transformations. So let's actually expand this a little. So we're gonna move this to make room for one more thing. So if we want to store the full information of this transform, then we're actually missing one thing. We're missing the position, right? like we've stored all information we need about the orientation of the object, but we haven't stored the position of it. So we need to do that as well. And so we're going to do that in the last column here. I'm gonna try to fit position in here. So in this case, that's going to be the position. So it is just the, so let's call it the P for position. So the X coordinate, the Y coordinate, and the Z coordinate. So again, X, Y, Z in this case are the components of this vector. Okay. Why not W? That's the standard. Because these are not components of a vector. Usually W is the fourth component, but this is not describing a component, right? These are just names for the directions right now. Okay, so now we have a 3x4 matrix. Which is really annoying that it's 3x4 and not 4x3, but for some reason everything's reversed and it sucks, but this is a 3x4 matrix. I don't know why they put the Y count first, but anyway. And so what's really cool about this matrix is that everything we did here to do the space transformation, everything we did in Unity with all of our dot products and local to world and world to local, and even the like relative vector stuff here and adding the position, all of that can be done using a single matrix multiplication, which I think is super cool. It's kind of beautiful that it's even possible to encode all of that in a single matrix. And so if we want to transform a vector using this matrix, all we need to do is multiply it by our the thing we want to transform. So let's say we want to transform a vector v from local to world. So then we have the x component of v, and then we have the y component, and then we have the z component. Then we need one more thing. When multiplying matrices, the width of the left-hand side has to match the height of the right-hand side. So we actually need to have one more thing down here. And so when we do this type of transformation, usually you would either have a value of 0 here or a value of 1. And what that does is that if we have a value of 0, you don't have to memorize all the matrix multiplication stuff, but if this is 0, long story short, that's going to cancel out or multiply all of this by 0. And so if this is 0, we're just transforming as a rotation. We're rotating it, but we're not translating it. But if we instead put a value of 1 here, then all of those will be multiplied by 1. And so we don't really have any vectoring components here. And so this is usually what you would call the W component. And you kind of just slap it on because you need to make the math work out. And so if you add 1 here, then this is actually a local to world transformation with the way that we've set it up with these specific vectors. And so this is local to world. So the vector v here is in local space. So the last component is like a bool that defines if you translate or not. Yes, exactly. So this whole multiplication is just a matrix representation of the actual code we wrote for 3b, right? Kind of, yeah. Except it's doing local to world, not world to local, but you can write local to world in terms of dot products as well, which is effectively what this is doing, right? V is not drawn on the thing. No, we haven't drawn V. But if we have a vector v, or I guess it's local to world, so it should be a local vector. If we have a vector v here, if we multiply that by the matrix, so this is in local space, we're going to get the world space vector here. So we can call that v prime. Okay. So now that the position and rotation, if we make it a 4x4, we can add velocity, yes? No, velocity is unrelated to this. Currently, time and physics is not involved in this at all. So this is it describes a transformation, basically, where we transform from local space to world space. Basically just the same thing we did here, but we're writing it in a much more compact format, right? Are x, y, z basically direction vectors for the local axis? Yes. We have 4 vectors here, right? We have a position vector, and then we have a vector for the y direction in world space, and the z direction, and the x direction. So this would be your transform dot up, this would be transform dot forward, this would be transform dot right. And so these are the vectors that we have shoved in here. And so this x-axis is this column right here. So we take the components of this direction vector and just slap it in here. And then we can build our matrix by putting our vectors in here as column vectors. So each of these, just plopping in that, plopping in that, and plopping in that, and so forth. Can we do the math? I think that would make it more clear. Yes, we could. I'm not sure if it would make things more clear, but so this position here, the 4th column is the position of this object. So the origin of the object is the last column here. So that's where the transform is located. So this would be transform dot position, and the XYZ components of the position. I didn't get the last column with 0 and 1. If this is 1, we're transforming it taking position into account. So when we transformed here, we usually have to do this first initial translation to make sure that it's originating from the object itself. If you set it to 1, you will take position into account. If you set it to 0, then what's going to happen is that the last column is not going to matter. And effectively, it's the same as doing a 3x3 matrix multiplied by a column vector with 3 components. And so if we set this to 0, it's gonna transform just the orientation, but not the offset. Because sometimes you just want to transform a direction vector or some other offset. Where the position doesn't really matter. You just want to rotate something to be in the same space of something else. So if position doesn't matter, then you can just omit the last part. Either just use a 3x3 matrix, use this one, or you can set the last one to 0. If this is the matrix if this is the only matrix you have available, right? Okay. What will the results look like? It will be it's the same thing as we did here. We just use a different method to get to that same result, right? Is there use cases for having W as a number between 0 to 1? I don't think so, no. I've never bumped into a use case for that. No, not for this one. I don't think I've seen that. I'm sure there is a use case, but I've never heard of it. Sometimes, well, depending on what you're doing, you sometimes end up with a value here that matters. but usually not in the context of just transforming vectors like this. So if you're doing rendering, you sometimes have a 4x4 matrix, which is what you usually use, where the last row has some funky projection parameters. And sometimes you get a value out of that in the fourth component that matters. And so if you're doing rendering, then the projection matrix quite often has a last row where you get a result where the W component has an important value if you want to do something like use it for a thing that's called a perspective divide, which is messy and has to do with homogeneous. I don't know the difference between those two words. Coordinates. Wouldn't 0.5 there just care for rotation and half of the distance? Basically, yeah. Yeah, it would multiply the position by 0.5 if you put a value 0.5 there. And like, I don't know what the use case for that is, so yeah. Oh, what would the results be? Oh, the result of this one would be a column vector. I guess I can do this. I don't know if you want me to write out everything, but basically this would be a column vector with 3 elements. Then this would be the rotated vector. So I'm calling it V prime. And so the end result is a column vector with 3 elements. Okay. Did that make sense so far? V prime makes me get derivation flashbacks. Oh yeah, sometimes it's, yeah. Yeah. It doesn't mean the derivative this time, so don't worry about it. So this is basically multiplying 2 vectors. It's a little bit more complicated than that. Effectively, what's happening? Like it's doing a lot of things. We can replicate it in this case on this website, right? So we have a 3x4 matrix, and then we have this column vector, right? And so everything that's happening is this. So it's taking this whole, it flips this whole column vector into a row, and then what it's doing, it's the dot product with the first row gives you a single number, right? And then it does the dot product between that and the next row, we get the next number. Does the dot product with the third row, and we get the third number. And so that's how matrix multiplication works. But usually you don't do this manually. Usually you just like use the built-in functions for that. Yeah, so this is what's happening. It can be a little bit tricky to wrap your head around, but okay. Did that make sense? Yes. Okay. Could you give an example of what value, for example, x, y might have in your picture? It's gonna be complicated because they're orthonormal, so unless they're like perfectly aligned. But for instance, there is something called the identity matrix. I don't know what happened here. Probably undid something. So let's say that you have no rotation at all. If there's no rotation, and maybe no position either, so maybe you have, then it's just going to be sitting at the origin with no orientation, right? It's just going to be at the default orientation. So we have the x-axis, the y-axis and the z-axis. Now, these axes have coordinates in and of themselves, right? Like the x-axis is a vector, and it would have the values 1, 0, 0. The y-coordinate would have or the y basis vector would have the coordinate 0, 1, 0, because again, y component is in the middle, it's pointing directly up, so this is the y direction. And then for the z direction, we have 0, 0, 1, because that's the last z component, and that is the direction it's pointing in. So these are the values for a something that has no orientation at all. But as soon as you start rotating this, these are going to get really messy decimal values, right? But so if you arrange this in the matrix, then let's see, let's just make a matrix again. So if you arrange these into the matrix, let's just try this one. Then we would end up with the values 1, 0, 0. And then we would have 0, 1, 0. And then 0, 0, 1. Right? And if we include the position, that would also be 0 for all of them. But if we just consider the rotation, this would be like no rotation at all. Because there's nothing has been rotated here. This is just kind of the default state. This has a special name. When you have ones in the diagonal and everything else is 0, this is called the identity matrix. So we can move that. This is the... Okay, so this is the identity matrix. It's the matrix that does nothing when you multiply with it. So if you multiply this by a vector v, that is equal to v. So it does nothing. It is similar to... So the word identity comes from the fact that it does nothing under a certain operation. So for example, if you have if you want to multiply a number, if you have x times v, or it's not a number, I guess x times a. If you want this to equal a, what is the value of x? And the value of x is the identity value. So for multiplication, the identity value is 1. So 1 times a equals a, right? For addition, if you want to have x plus a equals a, then x has to be 0, right? 0 plus a equals a. So 0 is the additive identity. And so what identity means is that it's the value that does nothing under a certain operation. So like some of you are mentioning, quaternion dot identity is a rotation that doesn't rotate at all. It's just the default rotation, right? And so that's what identity means in this case. It's just the whatever does nothing, basically. So that's where the word identity comes from. And so these are the values it would have if it has no orientation. Does multiplying a vector by this means having a scaled space? Yes, it does. So that's the last thing we haven't talked about in this yet, and that is scale. So in Unity, we of course have the ability to scale things, right? If we create a cube, then we can scale this one. And we can store this scale value inside of a matrix too. And the way that usually works is that, because we don't really have any more room to store the scale here, but what we can do is that we can change the length of the basis vectors. So if we make the x value, if we make this twice as long, then we've scaled it on the x-axis. And this will actually take that into account automatically. Just by extending the length of this basis vectors, we will automatically transform properly, taking that scale into account. And so the way that rotation, position, and scale is stored is usually in this matrix, where it just stores the orientation as 3 vectors. These vectors are then scaled by the scale of that object, and then the position is stored in the last column. And so this matrix fully describes a transform, or the state of a transform. So the x-axis basically holds only the x rotation, as in x equals 3.500. No, so none of these store angles. Angles are not involved here at all. So this x component is just a direction vector, right? The rotation and orientation of the whole system is just a side effect of the directions that these are pointing in, right? And so the x-axis, in this case, if we start rotating this upwards, like around the z-axis, then the value of this would start changing, right? Like it would start like, it would start decreasing here, so it would be like 0.9 or something, and then it would start increasing on the y-axis, and then it would still be 0 on the z-axis. So this is if we start rotating it. So maybe this would start rotating up like that. And so everything we're storing here is, again, it's just the directions scaled by the scale of the object. So is x just transform.right or 100? It's transform.right in this case. So for the local to world matrix, these are the world space directions of this object that are stored in this matrix. Can you use the identity matrix for world rotation if you would need to know the general world's rotation compared to yours? Your rotation should already describe that comparison, because the identity matrix doesn't do anything, right? So that is already what your personal rotation or orientation describes, right? Weren't we setting our world x using transform.right times local position x? Yes, we were. It gives the same results. We're just doing it in a different way. And if we had scale, it would be scale.x times transform.right. No, so transform, so it's similar to transform.right, but it's scaled by it in this case. So they're not exactly equivalent to transform.right and transform.forward, because those are actually, I don't know if Unity takes scale into account for those. I don't know if it normalizes them automatically. I kind of forgot, because I rarely use like non-uniform scale in objects. I forget if it's normalized actually. Okay. All right. Is transform.Euler angles calculated from the transformation matrix? I believe so, yes. I don't know all of the technical details in how it's done in the transform component, but it could be. And that's usually how I think about it. Like the Euler angles are not stored in the object. Unity's transforms, I'm guessing they either store it in a matrix or they store orientation in a quaternion. It's either of the two. But the point is that you can store all of that information in one matrix. And if you're in Unity, you actually have access to that matrix. So you can type transform.local to world matrix. And so this gives you the matrix directly. Okay. Any questions? Lots of typing. I need to drink. Several people are typing. Could you give an example of where you would need this in game dev? We use them all the time when transforming positions. And so if we want to know where something is relative to something else, we would generally use the matrix or the built-in transformation functions to do this. So for example, Unity has this built-in. So transform point. This is the same as the matrix times your vector, or v.y, v.z, and then with 1 as the w component. And so this is basically doing the matrix multiplication, right? And then there's another one, transform.inverse, transform point. And that one is doing the opposite. So that one has the inverse matrix, and then it multiplies the point there. Then there's another one for transform vector. Transform vector does not take position into account. And so these are basically the functions you would use generally when doing space transformations. If you want to go from local to world, you would use transform points. If you want to go from world to local, you would use inverse transform points. And this is basically the math that it's doing under the hood. It's taken the local to world matrix, multiplying it by our vector and setting the last component to 1 because we want to take position into account, right? So generally, these are the functions you would use when transforming from one space to another. Okay. Or actually, specifically, local and world. Okay, let's see. Can matrix be declared with any numbers, like matrix 4x3 instead of 4x4? Mathematically, yes, but Unity only has matrix 4x4 in its default library. Yeah, it has a few. C# has a few other ones, but generally you would use matrix 4x4. Okay. 2 questions. Can we program out local to world using matrices now? Yes, we can. What are the built-in functions in Unity convert between local and world? Oh, I already just talked about that. So this is the, if you're doing this in Unity, usually you would do it like this. If you actually have transforms to do this with. In some cases, it can actually be good to not have game objects like lying around your scene. If you just want, like, maybe you have a character with a gun, for instance. And so let's say you have a character and they are holding a weapon. I don't know what guns look like. This is a gun. And let's say they're holding this thing, right? And this gun could possibly be a game object, right? It has a position. It has the X direction. It's a little bit illegal to use X as forward, but that's okay. And it has a Y axis. And then there's someone holding this gun, right? They're holding that. So if you want to, for instance, if you want to spawn or if you want to raycast, like you're doing a raycast to fire this weapon, right? Maybe you don't want to raycast from the inside of the gun, right? Maybe you want to raycast at a specific offset. And so the barrel of the gun, or like the end of it, might have a local space offset, right? And so the raycast is in world space, but the offset to get to the tip of the barrel is going to be in local space, right? So you could configure this offset in local space, and then in order to get the raycast spawn position, to get this position in world space, you can use the transform function. So in this case, you would want to go from local to world, because the offset is in local space. And so then you would use transform.transform point, and then you pass in your local offset here. And then you get that position in world space. Sometimes people do this using like extra transforms, like you put an extra transform component here, just put another one, and then you use that to read your world space position. But there's some overhead to use the there's some computational overhead to have too many game objects in your scene because they have to recalculate every time you move something. And so sometimes it's good to not use extra game objects all the time. Okay. Wait, did I miss a question? Did someone delete a question? Oh, where do we use the transform vector method? Transform vector is effectively when you don't care about the position. So for example, let's see. Maybe you want to calculate, like a simple thing would be like you want a direction, but in a different space. What's a good example? I mean, you can have, let's say maybe you have some sort of spaceship. This is a spaceship, as you can see. Looks like this is going to turn into some Among Us thing. So if you have a spaceship, your spaceship obviously has some sort of position. It has a direction. Let's just use X and Y in this case because it's easier that way. So we have the X direction and we have the Y direction. And maybe you want to know what direction this is moving in relative to some other thing. So maybe you have another spaceship here that is just square. This is just square spaceship. This is the maybe these are the evil ones. Who knows? And so maybe you want to know like what is the direction to some other thing in local space, right? So let's say this is this ship. Oh, I actually drew this with the wrong coordinate system. Ah, geez. Oh no. I'm sorry. It's actually on the other side. Also a whole topic in and of itself. And so if you want to know the direction from this ship to this ship, then you could just do a subtraction like this and whatnot. And then you have a world space vector if you take the world space position here and the world space position here, right? But you might want this in local space so that instead of having this in world space, you would have this in local space coordinates so that you would know the exact like Y direction and the exact like X direction relative to this, relative to this ship, right? So maybe you want to use this as your coordinate system because then, I don't know, maybe you're making a game like FTL. Maybe you have like a whole crewmates running around in your ship and they're doing things. And they want to know where is the enemy relative to our ship. Because in their mind, their coordinate system is just local to their ship. And so this direction can be useful to know, like what is the direction to that ship? And it also would have to be normalized if we want to call it a direction. So let's make it a length 1. And so this is what you can use transform vector for, because we just want to transform the direction from world space to local space, but we don't want to transform the position, right? Because if we do that, then, world space would have an origin somewhere here. And then the vector from one to the other in world space here would be like this vector right here. And so if we transform taking position into account, we would get this vector pointing down there from the ship. But we just want to transform the direction. So we just want this direction in local space. And so we ignore the position of the object. And so that's what you would use the transform vector for. And transform vector is again the case where this is 0, where you don't take position into account. And so all you're doing is transforming the vector using the rotation part of the matrix. If the object is scaled, it's also going to take scale into account, but you usually don't scale objects, or at the very least, you usually don't transform using scaled objects. Okay, I hope that made sense. Okay. All right, how are we doing on break timing? Oh, yeah, we should go on break. Oh, what is m to the power of the power of 1? I guess I meant -1. I think I... There we go. That means inverse. So matrices are invertible. Well, not all of them, but these are. And so if you have a local to world matrix, what is my tool? There we go. If you have a local to world matrix, the inverse of that matrix is going to be world to local. So if you have a matrix M, then this is, in this case, this is going to be local to world. And then the inverse, usually denoted like this, is a world to local. Inverting a matrix can be expensive and complicated. And so usually you don't do that by hand. You kind of let computers do that for you. But yeah, so that's basically a way to get the opposite of that matrix. And the inverse, again, has the property of like if you multiply a matrix by its inverse, you will get the identity matrix. In other words, it's basically the zero of matrices, right? What does inverting a matrix mean, though? Is it negative? No, inverting a matrix is a more complicated action than that. Effectively, what it does is that you kind of flip the order of this. In other words, it's going to pretend that your local space is the world space, and then it expresses this, the world space origin, relative to this, as if this is our world space origins. That's kind of what it's doing. And so it's kind of just flipping the script. It's doing an opposite interpretation of the whole situation. And so, yeah, and doing that is non-trivial. I don't remember exactly how you do it, but we can look it up. Matrix inverse. There we go, an invertible matrix. Let's do Wikipedia. All right. There are many different ways of doing it. Which method do we want to use to... Let's see, inversion of 4x4 matrices. Here you go. Here's how to invert a 4x4 matrix. I don't enjoy doing that by hand, and I've never done it by hand, but you can do it by hand if you want to. And so, yes, to answer your question, you do need to calculate the determinant to get the inverse matrix. Yeah, but not all matrices are invertible, but all transformation matrices are invertible. Okay, I haven't talked about the last row. I'm just going to do that before we go on break. So it says matrix 4x4, right? It doesn't say matrix 3x4. So what is the last row? So this is mostly used just to cover almost all use cases in game development. The last row is rarely used in general. If you're working with like game objects in Unity, this row doesn't matter. You can just ignore it completely. So for most cases, this will have the values of 0, 0, 0, 1. Just like the identity matrix, remember that the diagonal is 1 and everything else is 0. And so this kind of fits into just the identity values. So this means that it's not going to contribute anything. This basically disables that row and makes it kind of ineffective, right? But what it does do is that it adds a fourth component to the result. So the result is going to be a 4x1 matrix. I always forget the order. It drives me insane. So this would be Vx, or the V prime x, the rotated vector, or the transformed vector, I should say. Z, and then you get some number here. In this case, it's just going to be 1. But usually you can just ignore that one. But the one use case where you actually use these numbers, it's a little bit esoteric. You don't have to remember it. It's when you make projective transformations. And so that is used in rendering. There are a lot of matrices that you juggle between. I do need to drink water, thanks. You juggle between a lot of different matrices. Like you have the model matrix, the view matrix, the projection matrix, and all of these things matter. And so the projection matrix has different values here. And that's usually used for like perspective transforms. So if you have a perspective camera in Unity, that one is going to use a matrix that has different values here. And that's going to basically create a skew transformation that transforms things in a very special projective way. Yeah. So basically all of our transformations that we've done so far kind of only support a very special type of transformation where you go from one coordinate space to a space that's maybe rotated, right? Like this is a transformation we support, or moving it or whatever. The projective transformation allows you to skew it like this. And so that's why it's useful when you're doing like perspective rendering. So this is kind of what the last row allows you to do. But in 99% of cases, you can kind of just not care about that last row. You generally don't really need it. Unless you're like doing some experimental projections in your camera. But in general, you're not going to touch that. But one thing that might be useful is that when you have a 4x4 matrix and you know that you don't have any like projective transformations, you can actually, there's a special function you can call to basically ignore the last row. So if we have a matrix here, it actually has a built-in function called multiply point 3x4. So this one ignores the projective last row. So this one is faster than a straight up multiply. Okay. All right, we should go on break. Let's see. Yeah, 10-minute break. Let's resume at 14:15. Does this look about right? I don't know what your rel.transform is in that case. Is that a different transform or relative object? Then all of the other ones should be the relative object as well. All of these should come from the same transform, not different transforms. And I think the one thing you might be missing is that all of the, I think transform.right might have to be scaled, but I'm not sure about that. But we can check, I suppose. If we just log transform.right. Yeah, it does not take scale into account. So you also have to be, you also have to include the scale in your diagram, the way you're writing it there. Yeah. Okay. How can you get local to world if you don't take in a relative object? All values will be the same. Oh wait, sorry, I misunderstood your diagram. I'm sorry. No, you ignore me. I think this is let's see. So the thing is that your matrix on the left is a local to world matrix, but the position in the column vector is a world position. And so if you want to make a local to world transformation, the position on your vector on the right should also be a local space position, right? Okay. Sorry, I misread it. But yeah, so it looks like transform.right does not, it looks like this one normalizes, so it doesn't just use the matrix directly. Okay. Yeah, we're taking a break. We're resuming at, oh god, caps. Resuming at, what do we say, 14:15? There we go. Okay. All right. Okay. Oh god, I lost the chat. Oh, there it is. How's YouTube chat doing? When we multiply a matrix with local position, does it automatically take it as a column matrix? Yes, I believe so. So if you have a vector here, I guess it would have to be a vector 4, right? So you would have some vector. What? I can't type right now. Then you do local to world matrix times vector. Then I believe this will... Maybe this is actually not valid. Does it not support this? Yeah, okay, I thought so. Yeah, so this does this interprets the vector as a column matrix, I believe. Yeah. Your video on Bezier curves, maybe choose that as the topic for the final paper we needed to write. Well, that's nice. I'm happy you found it inspirational. Okay, all right. What's the main use for rotating vectors? That's kind of like asking what's the use for rotating objects. You quite often need to rotate things in games. I don't know, anytime you want to turn your character, you have a thing you want to look in a specific directions, then maybe you need to rotate things. Still haven't even started talking about rotations. That's like a whole topic in and of itself. Do you have a format current line shortcut in Writer? I have format document, but not format line. I'm sure it's possible to set that up, but I usually format the whole document every time. I think I might have it on a custom shortcut, so I don't know what the default is. What if we make the matrix with vectors that aren't perpendicular? Then you will skew your space. It's basically a shear transformation. And so if you imagine your space kind of like a grid, kind of sort of something like this. And then you have your x-axis, and you have your y-axis. Then if you make them not orthogonal, you're basically going to do this to your space. Like this is the transformation you're then doing. You're skewing it like that. Doesn't it do it when you type the semicolon? If you have it set to format when typing semicolon, it does that, yeah. But it's a setting. I forget if it's enabled by default. Also, the W component isn't used for skewing, I think. Isn't it used to divide by Z when converting back from homogeneous coordinates? I mean, it's both, right? What happens to math if circles become squares? It's a weird question. I guess it depends on what the nature of how they become squares is, you know? Let's say if I were to only rotate an object 90 degrees along the y-axis, would the transform matrix become something like this? Okay. Here's the way that I tend to think about it. So, we have two spaces. Here are two spaces. I'm holding three-dimensional spaces. Then you can sort of try to reason about this, right? So let's say, well, what was your use case? So let's say this is our world space, and then you have another thing, and you want to rotate it 90 degrees along the y-axis. Okay, let's do y up. So 90 degrees around the y-axis in Unity would make this rotation. And so let's see. Would x be... Yes, x would be 0, 0, negative 1. That's true. And then y stays the same, and z points in... Yes, that's correct. You got it, Eric. That's how it would do. These are very, very useful when thinking about 3D rotation and orientation, which we should also talk about. I haven't talked about that too much yet. I'll do that after the break. Where's part 2? It's on my YouTube channel. Go to the latest videos, and it's going to be the part before this one. Okay. I'm very bad at taking breaks. I feel like I'm like, oh, I need to go to the bathroom, and then the time is up. If I wanted to try that rotation, how would I write it here? Which rotation? The one that Eric was talking about? Oh, yeah, you would basically type it in, right? So a rotation is just a 3x3 matrix. So if you want to ignore a position, you don't need the last column. But you could add it if you want to. But then the last component of your vector has to be 0 here, if you want to make sure to ignore the position, right? So this could be like any value, right? As for your rotation, then you would just put the numbers in that Eric had, right? So that was 0, 1, 0, and then -1, 0, 0. Yeah, and then you can do the whole thing. And then, oh, sorry, I'm not showing it on stream. Look, there we go. So you basically punch in the numbers, right, that Eric had. And then for your vector, you said 0 in the last one if you don't want position to be taken into account. And then that's what you get. And so now you've rotated this vector around that axis. Those are positions, right? So this is one position, this column. It represents the origin of the object that you might want to transform to and from. But in this case, we're ignoring that column because we set the last W component to 0. If you just want to do the rotation. And so if you just want to do the rotation, you can also just omit that entirely. So it's equivalent to doing the 3x3 matrix. So this would be the rotation matrix, right? Yeah. Damn it, a cat has been chewing on this. It's all beaten up now. Oh no. Okay. Are we ready to resume? Or how are y'all feeling? Am I ready to resume? Is it supposed to be -2 if it's a rotation? Yeah, like -2 is just the result of the fact that this one is 2, right? So because it's a 90-degree rotation, it's similar to just flipping a few coordinates and negating some of them. So what happened here is that it flipped these two and then negated this one, right? And so the 2 there is just because that's the coordinate that we gave it. If we give it the coordinate like 23, then it's going to say 23, right? Is the W in quaternions used to offset the position of the object in local space based on the new rotation? No, quaternions are very different from this. So no. We're going to get into quaternions as well. A little bit, at least how to use them, but what would 180 degrees look like? 180 degrees around the y-axis? So I guess that would be 180-degree rotation would be -1, and then 1, and then z would be -1. This would be 180-degree rotation, I believe. So this should just negate one of the components, I think. Or 2 of them. Oh yeah, 2 of them. Yeah. All right. Okay. Let's continue. Do you wanna see what it would look like if we used matrices to do these transformations? It's very straightforward, I guess. It doesn't really add that much, but basically we're gonna do something like this, right? So if we want to do, oh yeah, I should ping that we are resuming. There we go. React. Show me your presence. Okay, cool. Neat. All right. So it's a little bit wonky because here we're doing just a 2D transformation, but Matrix4x4 has support for like 3D projective transformations. So it's kind of like we're kind of doing a huge operation using tiny values, but that's okay. And so if we want to do this using vector 3s, let's do that conversion first. So let's just change to vector 3. Then we don't have to do that. And then we can change these. Don't need these two anymore. And then we need the z-axis on both of these. So z and forward. Okay. Oh yeah, we need to include the z component. All right, so now we just turn these into 3D transformations instead of just 2D. So the way you would do this using the matrices, so instead of, let's start with local to world. So instead of doing this whole thing, effectively you would do transform point, and then you pass in local. This is the short answer, and this is kind of what you use in practice when you don't want to do things manually, right? So this is what you're going to use for the most part in your games whenever you're transforming things, which is basically just kind of unnecessary to even have this function, right? So you would call this usually. But if you want to do this using matrices, you can do return transform dot local to world matrix dot multiply 0.3/4, then you pass local in there. So this is the cheap way of doing it, where you're skipping the last row, because this is a 4x4 matrix, but because transforms don't have any projective transformations, in other words, it never uses this last row. Oops, this last row. So we can call this special function called multiply 0.3/4 if we want to do a cheaper transformation. And again, this takes scale into account, which we didn't do here. So this is actually using scale. We can also do it using like the full multiplication, just straight up multiplying it by our vector, right? But here we need to keep in mind that there's no W component, and this is actually going to typecast it to a vector 4. And so this one is going to automatically set the W component to 0. So we might want to do make a new vector 4, where we pass in local x, local y, local z, and then 1, if we want to transform it as a point, right? Yeah, so this would do a full matrix transformation as a point, as in other words, it's taking the position of the object into account. Yeah, and so these three are basically 3 different ways of doing pretty much the same thing. So they're just using various ways of getting there. One big advantage of using matrices is that you don't have to have a transform in order to use a matrix. Sometimes you're transforming to and from different spaces where you don't have any game objects. You just have an orientation or a position somewhere that you want to transform to and from. And so you would basically use either of these 3. In practice, you use the first one almost in almost all cases if you have a transform, because this is the easiest function to call. Okay, and then world to local is effectively the same thing, except instead of using the local to world matrix, you use the world to local matrix. So if you want to do it the quick and easy way, you would use the inverse transform points. So then world to local is the inverse one. Or you can do it manually. You can do transform dot world to local matrix, multiply that by your, and then multiply that with the 3x4 multiplication with worlds. So you can do that too. So it's exactly the same thing here. You can use any of these. They all effectively do the same thing in this case. But yeah, so these are the options. There are many options to pick from. Okay. All right, so that's basically how you would do it in this case. You can also construct a matrix kind of manually. So you can make a matrix 4x4. Either you can, if you're feeling spicy, you can just like input the columns directly. But there's also a helper function called matrix 4x4 .trs. And so this one takes a translation, a rotation, and a scale. So you can construct a matrix using that. So you can give it a position. Maybe you want to place it at this position, and then you want to use a specific rotation. In that case, you would use a quaternion, and then maybe you want to give it a scale, and so you would give it some scale here. And so this gives you a matrix that effectively acts like a transform without ever having created a transform game object, right? Because game objects are heavy. You never want to like instantiate game objects just to calculate something and then delete it. That's very expensive. So quite often, if you just want to do the mathematical operation of transforming between spaces, usually you would do that using this matrix type. And this one also doesn't like allocate or create garbage or any of that stuff. And so it's very, very cheap to do this. Yeah, so that's ways you can use matrices. Very useful. Think of it as a transform without a game object, sort of. Okay, so that's how you would do these functions in many different ways. Okay, how much time do we have today? I actually forgot what we put on the calendar. Oh shit, not too long. Okay. Oh jeez. Ah jeez. It's gonna be tight. Maybe it's okay. Maybe we got this. All right, just need to drink some water. Any questions about matrices before we move on? Dead silence. It's all quiet in the library. Oh no. It's either very good or very bad. Everyone is like, I didn't get any of that. And then I'm like, oh no. Ah, jeez. Some typing. Not at the moment. Will you be available tomorrow for help with assignments? Technically, no. Practically, I'm probably going to be a little bit present. But I'm not going to be able to do like joining for calls and whatnot. But I'm not technically scheduled to be present, but usually I will be a little bit present every now and then. Okay. I need to drink more water. I'm so dehydrated. Lots of typing. Any situations where it's better to build matrices yourself to handle these transformations, or is it generally the case where you trust Unity's built-in methods? Yeah, anytime you don't have a game object, I would recommend using matrices directly. For example, I'm just going to pull out a use case that I've had. Let's say that you are making a game, just purely hypothetically, not that anyone would do this. Let's say you're making a game that has like splines. So in this case, this would be like a Bezier curve, right? It has a starting point, has an end point, and then it has the smooth shape along the spline, right? So in terms of game objects, maybe you just have a game object at the end and at the start. But let's say you want to get a coordinate space at an arbitrary point along this thing, right? So in this case, maybe you want an x-axis and a y-axis at a specific point on the spline, right? And then maybe you want to use these coordinates to generate a mesh. Maybe you want to generate like a some sort of railroad mesh or something like that, right? That means that you're going to need to calculate the, you're going to need to go from local space coordinates that define the profile of this railway to world space coordinates to generate the mesh, right? And so in this case, when you sample the curve, ideally you would get a matrix out of this. You get a matrix here, and then you transform maybe like 10 different vertices here along this profile. And then you do the same thing for the next part. So for the next segment, you get another matrix representing the orientation of that point in the curve. And then you use that matrix to transform a lot of things from local to world, and so forth, until you've built an entire mesh that goes all the way to the end. In this case, using a game object is just going to be wasteful and kind of weird, because then you're going to have to like move the game object in between every generation and whatnot, which is kind of clunky and strange because it's kind of just a temporary placeholder. And so instead of using a game object, you can just use the transform, or the instead of using the transform, you would use a matrix. So then you would construct a matrix from the values you get out of the sampling the curve, and then you can just use that. Flowstorm reference? Yes. I'm surprised any of you have even heard of Flowstorm. But yes, I used it in my game, Flowstorm. Do 3D modeling programs use matrices for making meshes out of splines? Most likely, yeah. I'm not entirely sure how you would do it otherwise. I mean, you can do it using the manual way that we did it here, where you're kind of doing a matrix multiplication, but we're just not calling it that, right? I could show you my use case if you're interested in seeing my game, but I don't want to go too much on a tangent. But I can show it if you want to. If not, I'll just continue with the lecture. Someone asked another question earlier about rendering that I could also talk a little bit about in the game. Okay. I only got one response. I don't know. I'll try not to go too far on a tangent about that. Does it even compile? I'm not sure. We're already in overtime? We're not in overtime right now. We have 1.5 hours left. There's not that much more content for the assignments, no. So I think we do have time. Okay, this is a game that I've been working on for way too long. 12 years ago, I was a student at FutureGames, and I started working on this game when I was at FutureGames, and then since then I've scrapped the entire project and rewritten it from scratch 3 times, I think. And it's not even near finished, but and I also have to launch Steam because I've hard-coded Steamworks into the game. It actually doesn't work if you're not running Steam because I'm a professional. Okay. There we go. Okay. So this... Actually, do we have audio? I don't know if we're gonna get audio. We'll see what happens. Okay, there we go. This is a game that I've been working on called Flowstorm. Audio is muted. Oh, we do have audio. Good. Okay, this is a game that I've been working on. It's a little rocket ship game. And it looks like this. It's like a little racing game. Ow. I died. Anyway, so this game has a level editor. So if I go to here, create a new thing. And this level editor is based on Bezier curves. And so you can kind of create your own levels like this. And so these curvy sections are 3D meshes. So if we go into the scene view, you can see that these are meshes. And so when I generate these meshes, they are generated along the curve. But at each point in the curve, I need to sample multiple vertices, right? Like these vertices along this whole edge, all the way around here. Like this whole section, all of the vertices here, they have to transform using the same matrix. And so it's just easier to make a matrix and then transform using that rather than juggling game objects, right? And then, yeah, and so then that's how it's done. And so all of this is procedurally generated stuff. Yeah. It's a lot of polygons. How is the performance so good? It's not that many polygons compared to most games. Like, it's a very minimalistic game. And so this is fine in this case. And yeah, so this, if we put it side by side, so we can look at this directly. And so if I modify this one, you can see that it updates the mesh. And so this is all done using this type of matrix transformation. Yeah, and when we were talking about the dot product, I mentioned the audio for when you're hitting the ground at a specific velocity. And so I do that in this game. And so if you consider the impact sound when you hit the ground, that was pretty loud, right? But if we're not moving very quickly or at a very shallow angle, it's not as loud. Like this is pretty quiet. And so the impact sound is much louder if you hit hard, but if you don't hit very hard, it's much weaker. And even if you're moving fast, it's not going to be loud. And so, yeah, so that's where I use the dot product. I use the dot product with the impact normal and the velocity of the ship. And so by then, I can calculate the what I think the volume should be given those parameters. And that's all using the dot product. Yeah, I also use a dot product for the pitch of the audio. So for example, if you do have audio, right? You can hear the game. I'm not sure if you can actually hear the game, but you should be able to hear the game. Okay, does this sound, is this louder than my voice? I don't know if it's impossible to hear me. I don't know. It's good. Okay, it's audible, so you can at least hear something, I hope. So the I also use the dot product for the audio for the engine. So if you listen to the audio, you can hear that it changes pitch when you accelerate, right? But not only does it change pitch when you accelerate, but that acceleration is also relative to the direction you're already moving in. And so if you listen to it, if I start moving and then I change direction, so it's kind of, I do the dot product between the current velocity and the direction you're accelerating in. And so you get this more dynamic sound where if you're moving perpendicular, it's kind of like you're starting over, accelerating. And so it sounds way more interesting, right? Also, my lighting system is a little bit work in progress, as you can see. I'm not using Unity's lighting here. I'm kind of doing my own thing. You can hear the audio there. And so if I start moving perpendicular, it pitches down again. And so what you're hearing, the pitch of the sound, is actually not the speed of the ship. The pitch of the sound is the speed of the ship in the direction you're pointing. And again, that's the dot product. You take the velocity, project it onto your direction, and then that's the value you get out of the dot product. You get the speed in your direction. That's the pitch, with some like range remapping and whatnot. The dying is so satisfying. I don't know, it's just a stock sound of a plate shattering or something. Or check out the dot product for the collision to decide if it's destroyed or not. No, that's just, you always get destroyed on collision. It's a very mean game. But you could use the dot product to figure out the impact force, yeah. But yeah, you can die just by touching. You don't have to move quickly at all. But yeah, so that's the game, and then that's how it works. And then have this whole lighting system, have little underwater lights. So this is kind of like a custom render pipeline. I don't really use Unity's render pipeline for this, and so I kind of made my own thing, for better or worse. Yeah. But can we playtest it? I mean, I guess, but it's kind of broken. If you really want to, I can get you a build. But yeah, anyway, that's the game. All right, there we go. That was all I wanted to talk about when it came to Flowstorm. Use cases. Imagine that. All right, let's see. What do we got next? Oh yeah, we have two things. So when we talk about coordinates in general, I've sort of been assuming a lot of things. And so there's one thing that you should keep in mind whenever we talk about coordinates in 3D. And that is that shit's complicated. It's not very straightforward, these things, because all of the different applications use different conventions for how they determine what should be up in your coordinate system and whether or not it should be left-handed or right-handed. And so here's a chart I made a while back. If you want to know which is using which, it gets complicated. Sometimes you import models from Maya into Unity, and then all of a sudden your things are mirrored. Or you're importing from Blender, and then they're not only mirrored, but they're rotated as well. And so this can get a little bit complicated. And so some of the, sometimes you make assumptions about what axis refers to what. There are a few things that you never make assumptions about though. And so one of the things that is always consistent is that if you consider the vectors, you have x, you have y, and you have z, right? You might notice that I'm using colors for these, right? The colors are always corresponding to RGB. No matter what application you're using, they will be corresponding to, you know, X is red, Y is green, Z is blue. Every application follows this. So that's consistent all over all of your applications. What's not consistent is which of these it considers to be up. It's also not consistent whether or not it's left-handed or right-handed. And so the difference between left-handed and right-handed is that you can sort of use your hand to create this coordinate system. So if you imagine your thumb is the x-axis, then you can just go in order of your fingers, X, Y, Z, right? And so you can kind of create your own little gizmo like this, right? And so if you have a left-handed coordinate system, then your left hand would be able to do this when forming your thing. So this is a left-handed coordinate system. If you have a right-handed coordinate system, then you would do it with your right hand instead. And these are actually mirror images of each other. And so you can't directly convert from a left-handed system to a right-handed system. It's a little bit complicated how that works. But yeah, so looking at this chart, Unity is left-handed, and it has decided that Y is up. But for example, Unreal has a different up direction. Unreal says that Z is up. I think Unreal also uses X as forward, if I remember correctly. Unity uses Z as forward. So there's a lot of assumptions made in what we call up and what we call forward and what we call right and left and back and so forth. So it's a good thing to keep in mind because sometimes it's different. Okay, so Unity is a left-handed, uses a left-handed coordinate system, and in world space, the y-axis is up. Good thing to keep in mind. All right, and so now that we're equipped with this cursed knowledge, we are ready to learn about the cross product. I don't know where to put the cross product. Okay. And so the cross product between two vectors, so we have a vector A, is written with an X like this. So this is the cross product. And then that would, and that is distinct from the dot product because the dot product uses this dot symbol. And so that's the dot product. All right. So this is dot. And this is the cross product. Okay. So the cross product is actually a very strange type of operation. The cross product kind of mostly only really works in 3D and 7D, I believe. And so it's kind of a strange operation. Generally, if you do things in other dimensions, you use a different operator. But in 3 dimensions, it just happens to work out to be this useful thing that we use sometimes. And so the cross product, a quick way to describe the cross product is that it gives you a vector that is perpendicular to both A and B. And so what that means is that if you imagine a 3D space Here we go. This is a terrible grid. Here we have a grid. It's beautiful. I hope you like it. Okay, so if you have this grid, it's a coordinate system. So if you have a vector A here, vector A, or no, sorry, we're gonna do this, or no, that's fine. We have vector A, and then we have a vector B, just gonna draw it there, call that B. Then the cross product will give us a vector that is perpendicular to both of them. And so this is the result of the cross product. We get a vector out of the cross product, so we can call that C. And so this is equal to C. And the direction that this one is pointing depends on the coordinate system that you're using. So if you're using a left-handed coordinate system, then this would point upwards. If you're using a right-handed one, it would point in this direction. And so the result of the cross product, the way that we visually interpret that result, depends on the handedness of your coordinate system. But the point is that it gives you a perpendicular vector. And so if you have your coordinate system, you know how we talked about here, how we had these three basis vectors, right? Let's maybe shorten this one again so we don't have a cursed space. And so if you take the cross product between x and y, you get z. And so that's a very useful concept. So now you can kind of go from a 2D space to a 3D space like automatically, right? So the cross product, or actually we should just write it as x cross y equals z. So A cross B equals negative B cross A. Yes. So if you flip these two, so if you use B instead of A and A instead of B, then you get a vector pointing the other direction. And so, like someone said, that A cross B equals negative B cross A. And so, unlike the dot product, the order matters for the cross products. And this property is called, it's anti-commutative. So commutativity is the property that you can swap the components or the order of operations. But for the cross product, you can't do that. It doesn't give you the same results. In fact, it gives you the exact opposite results, and that's why it's called anti-commutative. Regular numbers are commutative because like 5 times 2 is the same thing as 2 times 5, right? But that property doesn't hold here. And so numbers, just regular multiplication with numbers is commutative, but the cross product is anti-commutative. Very important to remember, especially if you just got things wrong and you just want to flip it to the other side. You can just flip the components or the input to that function and it's going to flip. How do we know which result we're getting? So this is where you can use the left-hand rule if you're using a left-handed coordinate system. If you use your hand, should probably switch camera. If you use your hand, you use your thumb as the first component in the cross product, and then your index finger as the second component, and then the middle finger is going to be the result of the cross product. And so you have A, B, C. So A, B result, and that is going to follow the same rule as for X, Y, and Z. And so the cross product between my thumb and my index finger is going to be the middle finger. If I change so that they're not perfectly perpendicular, my index finger or middle finger will actually shrink the closer they are to each other. And so I can actually show you a visualization of this. Worst gang sign. It's not west side or east side anymore. It's right side and left side. Where's my... Why? How did you find my own tweet faster than I could? William, I hate you. I mean, I don't, but thanks. Anyway, here's a visualization of the cross products. And so, I don't know if I can zoom in more on this. Yeah, so this is doing the cross product between A and B, and C is the result of the cross product. The number here is showing the length of that vector. And so you can see that it has a similar kind of vibe as the dot product when the vectors are normalized, where you kind of get these values from, 0 to 1, and you can use that to measure certain things, right? Yeah, so this is what the cross product does. The cross product between the red one and the green one gives you this blue vector. One thing to keep in mind, if they are pointing in the exact opposite directions or exactly the same direction, in other words, if A and B are parallel, the cross product is 0. Yeah, so that's what the cross product does. So it's very useful anytime you have two vectors and you want to get a perpendicular vector to that vector, you can use the cross product to do that. Okay. All right. Hope that makes sense. So that's what the cross product is used for. You can get a third perpendicular vector to your first two vectors. Just gonna clean this up. Is it empty, really? You're empty, Photoshop. Oh, you bookmarked all of my math visualizations? Jeez. Didn't think anyone used that page. Okay. That's the cross product. And so, maybe we should use this in Unity. Show a little use case. Are the tweets made with shapes? Most of them, yes. This one, I believe so, yeah. All right, how are we doing on time? Okay. Oh, we should do our last break, right? Final break. And then, okay. Is it left-hand rule for cross-product universally? No. The left-hand rule is specifically for left-handed coordinate systems. And so which rule you're using depends entirely on which application you're using. And what's kind of fascinating is that the math for calculating the the cross product is actually the same, regardless of if it's left-handed or right-handed. The math is exactly the same, but the way it's visualized depends on a lot of assumptions. And so the math doesn't really care about left or right-handedness, but when you show it on screen, that's when it's going to start to matter. And we actually didn't talk about how to do the cross products. It's a little bit messy, but yeah, I can write it out if you want to, but it's pretty long. But it basically, oh geez, I always forget. It's A, the y component of A multiplied by the z component of B. And then you subtract the z component of A. Multiply that by the y component of B. So this gives you the first number. And then you basically continue like that. So it's the z component of A, it's the x component, and then it's A x, I believe, and then A y, and then we have B x, B y, B z, and finally B x. Okay. So this, if we write it as a column vector, this is the results of the cross product. If you want to calculate it manually, which I have never done, because it's kind of a mess. So this is how you do the cross products. And so it's basically this. Okay. All right, so the math for this is the same regardless of left-handed or right-handed, it just doesn't matter. Okay, we should do break until 15:10. So we're resuming at 15:10. Oh yeah, my math visualization website doesn't work in Firefox because there's some sort of course security setting that works differently in Firefox that makes it so that it can't embed tweets using Twitter's own integration thing. It's just weird. I don't know. I can't be bothered fixing it. I'm sorry. All right, so we're on break, so we're gonna resume in a bit. Okay. And the cross product is a strange one, but it's useful, but it's strange. We're gonna get into a use case for this after the break. I should probably go to the bathroom while we're on break. So the thing about how mathematical formulas were discovered, one thing that I find super fascinating about math is that vectors are a pretty modern concept. Like quaternions predate vectors, even though quaternions are like way more complicated in our view because we're so used to dealing with vectors. But like quaternions came before and they were like supernatural for a long time, which I think is kind of weird. This whole thing about coordinate systems and vectors and dot products and whatnot is pretty modern. It's kind of weird. Why are quaternions somehow more the more advanced archaic ones? Because they had a very, very strong focus on algebra and not a very strong focus on like spatial relationships in virtual worlds. And so I feel like it's probably like a use case difference. All right, let's see. How are we doing on break time? Okay, a little bit more. Any questions, thoughts? I was kind of hoping we would have time to go through trigonometry today, but we don't, I believe. Unless we speedrun trigonometry. But I don't want to do that. Okay. How's YouTube chat doing? Is YouTube chat doing okay? Talking about Firefox. Quaternions are one of those mysteries of the world. Yeah. It is a mystery. Experimented with the cross method on Android gizmos. Is there a certain function to use, or do you do 3 separate floats of? You would generally use a built-in function. So there is a vector3.cross. So that gives you the cross product between your vectors. So that's what you would use generally to calculate. Will we talk about how to use time.delta time correctly? Yes. Wait, did the stream die? Did it just die for Anton? Oh, it's back. Okay, we're good. Yes, we're going to talk about frame rate independence. So yes, we're going to do that. Okay, it was off for a little bit. Strange. Oh, can't believe you matched your cat ears with your hair. That's so cool. I mean, your ears generally match the color of yourself, right? So I don't know. That's just kind of how nature works, right? Okay, all right. I think we're ready. We're ready to continue. Presence check. Being weird on your end too? That's strange. I don't know what to do about that, so I guess I'll just continue as normal, and if it keeps getting like unwatchable, let me know. If it's like cutting out important stuff. Okay, Yeah, I don't know if it's on my end or if it's on YouTube's end, or I'm not sure. Yeah, hopefully the VOD will work. The status looks fine on my end. YouTube says everything's fine. Okay, you're all here. Good. Okay. I wish we had a little bit more time to talk about rotations. I think we can maybe do it a little bit today. You know what? Let's do a little bit of rotations. We haven't even talked about angles yet, but maybe that's okay. Or no, that gets into trigonometry. I don't know. Let's do a use case for the cross product, because we just talked about the cross product. Just making sure I didn't miss any questions. I've forgotten a lot of math from high school. That's why I'm going through all of this, because you tend to. Okay. Wait, is there a 2-minute delay? That would not be good. Okay, someone type bananas in chat. Quickly, now. As fast as you can, just to test the stream delay. Go for it. Okay, yeah, that's not 2 minutes. And now we just confuse the hell out of whoever's on a longer delay. Okay, cool. So it seems fine in general. All right, so let's see. I guess we should just clean up this whole thing a little bit. Okay, you're good now. Reset the page. Everything's up to speed. All right. There's so many bananas in chat. Jeez. All right. So I'm bringing back our little terrain situation here. Excuse me. All right. Let's actually bring some lights into the scene because it's kind of hard to see 3D geometry. Create light, directional light. Perfect. That's too intense. Let's reduce this a little bit. There we go. Okay. So I'm just creating a rough approximation of a terrain right now because I don't know how to use Unity's terrain tool because I never make terrain in Unity. And so we're just gonna not use that. So we're making a very fluffy, cloudy, cartoony terrain here. Maybe throw in some cubes, cause why not? All right, because now we're doing 3D stuff, and it gets a little bit more complicated now. And so, let's say that you are, let's say that you're playing a game like Overwatch. I presume some of you have played Overwatch, many of you familiar with it, or maybe Team Fortress 2. That also works. In both of these games, there is a class that has the ability to place turrets on the ground, like little automated robots that can fire at people, right? Like little guns that they can place on the floor. And so let's imagine this being the turret. We can create a child object here. Doing some turret guns. These are guns. Just imagine that these are little pew pew guns. And so guns. There we go. Actually, the orientation of this is terrible. Need to fix the orientation. Let's fix the scale too. There we go. Create a child object. I know how to click. Don't judge my clicking. Neat, we did it. This is a little turret. If you are playing a game like Overwatch or Team Fortress 2, like any game where you have a character that can place a little automated turret somewhere, maybe the turret only has a limited angle it can fire in, right? Maybe it can only turn a certain amount. Like maybe it can't turn all the way back, right? And so the direction you place the turret in matters a lot, right? But what if the surface you're placing the turret on, what if that surface is rotated? And now you want to place a turret on that surface, but what orientation do you pick for this turret? Because when you're aiming on the floor, you probably want to pick some smart rotation for this turret, but what should that orientation be is kind of the question, right? And this is a use case for the cross product. Because now we have a set of vectors that we want something to be perpendicular to, but we also want to constrain it to another direction. And so this is, I'm going to show you a little use case for this. Let's just change the pivot point to this one. To be on the ground. There we go. There we go. Okay. So now we have this little turret placement problem. And so let's solve this. Let's see if we can work it out. So if we create a game object, we're going to do a similar thing as we did before, of kind of like the laser, where we have a game object that shoots a beam, and that's going to represent the direction the player is looking. We could make it so that we use the camera when hitting play mode, but that seems like it's annoying. I guess we could use the camera directly. Let's do that, I think, instead of an empty game object. Where is the camera? There we go. So here's our player camera. Beautiful. So this is going to shoot a laser to place the object. Okay. Let's remove the colliders from the turret to not interfere with our raycasting. All right, I'm going to add a script to this. So this is going to be called the turret placer. Come on, writer. I believe in you. We're going to keep using our trusty on-draw gizmos. It's so nice. I don't like having to press play. All right, so now we're going to raycast from the center of the camera. So the center of the camera is basically going to be where the player is looking, right? That's where you generally place the crosshair in an FPS game. And so when you activate the turret, you want to place the turret where you're looking. And so we're going to use that to get information about the surface. We're going to raycast through the middle and hit the surface. And so we've done this before. So physics.raycast. And the origin is going to be, I guess we can set up array. Rat. Transform dot position, transform dot forward. So forward is the z-axis. Cameras have the z-axis forward. Good thing to remember. So forward is going to be the direction of the ray. And then we're gonna raycast, and then we want to get information about that. So we need the raycast hit. Yeah, I'm sorry, I deleted the rat. All right. Okay. So, now we need to figure out how do we want to place this turret. We can start pretty basic to just like, let's just put the turret at the position. Then we're going to need a reference to the turret. So that's a transform turret. We're also going to need to make sure that we have it assigned. Otherwise we don't want to do anything. Okay. Let's recompile. Select our little turret. And then we're assigning that there. All right. So now we're going to do turret.transform.position equals the hit.point. So we're just moving it to that location now. This is kind of the first step to doing this kind of algorithm, right? So there we go. We have a turret. Maybe we can do split view for this. Really, Salad? So now if we look around, you can see that the turret is sort of adapting to wherever we're looking. So now we kind of have a first step. This is getting close to what we want, but obviously it's not perfect because it's not looking the direction that we want it to look, right? But if we wanted to look the direction that we are looking in, we kind of run into a little bit of a problem. So if we make it just look directly in the same direction as the camera, it's going to look into the ground, right? And we generally don't want it to do that. We want it to be aligned with the ground. But in this case, it's just not going to be aligned at all, right? And so if we set the rotation as well, so it's a turret dot, oh, I guess the turret is already a transform. So turret dot rotation. We haven't talked too much about rotations yet, but long story short, one way you can create rotations is using the quaternion class. And there is a quaternion class or quaternion function called look rotation. And so we can just set it directly based off of some direction we're looking, right? And then let's see. So we can use the direction of the ray. That's what we wanted to use, right? So ray.direction. Didn't we discuss something similar yesterday? Projection planes? Yes. This is related to that. Okay, so we recompile and see what happens. So now we've set the turrets to use the same, pointing in the same direction as the camera. Obviously, this is not really what we want either, because now it's not flush to the ground. We want it to be aligned with the ground, not like pointing down into it. Like if we're looking down like this, we still want it to point forward, right? Okay, and so this is where the dot product, or sorry, the cross product has a very good use case. We can start reasoning about our problem on paper, as usual, because that is a very good place to start. Okay, it's a little bit complicated to do this in 3D though. Trying to think of how I want to draw this. We could possibly do it sort of in 2D. So let's say you have some surface and you have your camera or an eye looking somewhere. And you want to place a turret at this location. And so what we want to find is that we want to find the directions that would make sense for this object would be a vector that is pointing forward like this. This is kind of what we want, right? We don't want it to point into the terrain. We don't want it to be completely flat. we want it to point along the terrain, right? So this is going to be our forward vector or our z vector. So we want to find that somehow, right? Okay, so what other information do we have about the surface we hit? Well, we have the normal direction, right? And the normal direction, that's what we want to be our up vector, right? Like this is the direction we want to be, the turret should be pointing up at, right? So this is our y vector. But then we're still left with the problem of what orientation do we want around y? Because again, on a 3D surface, if this is, some sort of surface, then the rotation around y could be anything. Like we can't just align with the normal. We also have to decide somehow which direction this should point at, because we want the turret to point forward, right? Okay, and so what we can do here is that we can actually utilize the cross product between the direction we're looking at. So this camera has a direction, right? And so if we take the cross product between the direction we're looking at and the normal of the surface, we actually get the x-axis for this. Let's see, z, y, then x would point toward the camera, I suppose. So then we would get the x-axis because the x-axis, now that we get from the cross product between the kind of the view vector or the camera vector, because it's perpendicular to the normal, it's guaranteed to always point along the surface. Because the normal direction is always 90 degrees off, and because the cross product gives us a vector that is perpendicular to both of them, it has to necessarily be along the surface itself. So that is usually called tangent to the surface. So if you imagine a 3D surface, that's a very extreme angle. If you imagine a 3D surface like this, usually what we call the normal vector is pointing directly out from the surface. That's a normal. And then a vector that is pointing along the surface is called a tangent. And there are an infinite number of tangents. You can pick any vector pointing along this circle right here, and those are all tangent to the surface, right? And so the cross product will give us a tangent vector based off of our viewing direction, right? And so we can use this to get, to start constructing a coordinate space, right? Yeah, and so in some cases you have a canonical tangent, a tangent that we've defined to be the tangent. In that case, you also have another vector that is perpendicular to both of those, and that's called a bitangent. Mostly shows up in rendering, if you're into that. Oh wait, this is the wrong way around. Shit, this is a right-handed coordinate system. I'm sorry, I messed up. I don't know how to erase this now. I have to erase the entire word. Oh no. I think, right? Yeah. There we go. Okay. All right. Anyway, so we can start here in order to construct the orientation for our turret. Okay. What's a bitangent again? The bitangent is the cross product between the tangent and the normal, and it is perpendicular to both of them. And so it's kind of the coordinate system, the basis vectors of the coordinate system that we usually call tangent space. Isn't it also basically tangent though? Yes, but sometimes you have a canonical tangent that we kind of name the primary tangent. And if you have that, then you also have a bitangent. So again, in rendering, this comes up a lot. If you're doing normal mapping, you need the concept of a tangent and a bitangent direction. Yeah, so if you're using normal maps, this is a thing. So the bitangent is a tangent in and of itself as well. It's just that it has a special name if we have a canonical tangent. Okay, so the new forward we want would be the bitangent of the normal tangent. That might be the case. I actually haven't thought through this problem too much. So that might be true. I'm kind of busy just putting out all the information. So let's draw them. Let's do some math. Okay, so first off, we might want to draw the normal. So okay, let's use draw ray this time. So we're going to do hit dot position or point, and then we're going to do hit dot normal. I also want to draw the line from the camera to the point we hit. So draw a line between, let's see, the script is on the camera, so transform dot position. I guess we should do ray dot origin, and then hit dot point. Okay. Okay, let's color these by the axes that we want for the turret. So we're going to make this one green. Because we do know that we want the y-axis to be pointing directly out of the surface, right? And so we have one of our axes down already. So that's hit dot normal. So we can actually just type that out. So we can do vector3 y-axis, and we'll set that to hit dot normal. And then we can draw our y-axis there. And then we want to draw that one. Let's set that one to white. All right. There we go. We can see that it's hitting the surface. And then we get the green line is the normal there, right? And so if we move this, you can see that the green line is changing, hopefully. So we're moving this along the sphere, just like we did with the laser. We're getting this information about the direction out from the surface itself. And so now what we can do is that if we do the cross product between the direction we're looking in, we're a little bit rotated now. Geez. Oh no. If we do the cross product between, I don't know how to fix my rotation. There we go. Euler angles. I don't like this. So now if we do the cross product, we actually get a tangent to that, a tangent to both the direction we're looking at, and the, or something that's perpendicular to our look direction and the normal. So let's do that. So vector 3. And so that will actually give us our x-axis. So vector 3 dot cross. So we're going to do the cross product. And let's see, I need to think now. So if we, again, use the left-hand rule to figure out which direction it should go, we want it to point right. And so if the A input is that the look direction, then let's see. So this is the look direction. This is the y-axis. Then we're going to get it pointing left. So we want to do it the other way around. So we want to do normal cross look direction. Should give us the x-axis here. So hit dot normal. And then we have the y-axis, which in this case is the normal too. But also keep in mind that the no, wait, sorry, not the y-axis. Where we're going to do the cross product between the ray direction. Sorry, the direction of the ray. I think was that the order? No, it was the other way around. Y-axis and then the direction of the ray. I think. Yeah. Okay. And so let's draw that as well. Reted. It's a new color. Let's draw the x-axis first, just to keep things in order. All right. There we go. So now we have an x-axis here. There's one more thing we need to take care of though before we move on. If I rotate this one so that it's a very shallow angle, you can see that it's very short, right? So this is not normalized. The cross product makes it shorter the more similar the look direction and the up vector is to each other. And so we need to normalize this. And so we can use the property .normalized. So now if we make this shallow, and then if we recompile, you should see this one changing length. There we go. Okay, so now we have some sort of x-axis. So the one thing we're missing now is the forward direction. We have our up direction, we have our right direction, but we don't have forward. But, like I mentioned before, if you have... it's somewhere here. If you have two perpendicular axes and they're normalized, then if you just do the cross product between x and y, you get the z direction. And so we're just missing that one cross product. And so we get our z-axis, which is forward, by doing the some typos. So we do the cross product between the x-axis and the y-axis, and then since both of them are normalized, we should not have to normalize it. If they're already orthonormal, as in they're orthogonal and normalized, the cross product is also going to have the length of 1. So this should give us the z-axis. So let's see if that works. And there we go. You can see that we have built a little coordinate space now, but we need to apply it to the turret because the turret doesn't use it at all right now. We probably want the turrets to, you know, actually use that orientation. And so we can use our trusty look rotation again. But now we can supply the forward and up vectors directly. Because now we know the z-axis, and then the up direction, in this case, is going to be the y-axis. You don't really have to know too much about quaternions. You can sort of just know that this function gives you an orientation given a forward direction and an up direction. So now we should have a turret that is reasonably oriented, except it's offset by 90 degrees. Because, did I use the wrong ones? Maybe it's the wrong order. Oh yeah, I put the x-axis. It should be the z-axis. So z and y for the look rotation. Okay, there we go. We got our turret. And so now if we move this around, you can see we're getting a way more reasonable placement for this, right? Like it's kind of pointing forward, but it's still aligned with the surface, which is really important for us to do, right? Yeah, and then we have some roll that keeps happening. Yeah, and so this is just one way you can start doing these types of alignment things. All right, and that's kind of what the cross product is often used for. This process, I believe, is called orthonormalization. I think it's the Gram-Schmidt orthonormalization, something like that. You can Google it, and you'll find something along these lines if you want a mathematical definition of it. Would you have to do a special case for when the incoming direction and the normal are parallel? Yeah, so it kind of depends on how you code this. There's not really just one answer for how you should orient this. Like for example, you could make it orient to the camera up vector instead, because you can see that it's sort of slightly off kilter if we wanted to point more directly forward, right? So you might want it to point more like this. So then you have to align to different vectors. But yeah, quite often you do have to special case once you start looking too far down, because then you get pretty strange results, right? Yeah. Yep. All right. I think that might be... Yeah, that's about all we have time for today. So we should think about... Could we not use projection planes here? You could probably if you want to. I think that would work too if you want. I would just solve it with cross products instead, but you can do it the other way around as well. All right, so I think we need to figure out some assignments. I actually don't really know what assignments to give now. Oh no. Usually the turret is the assignment. They're the same thing implemented differently. I mean, quite often you can get to the same result using different methods. That doesn't mean that they themselves are the same thing. So usually there's many different ways of solving this. Like again, there's not one right answer for how we want to do this type of thing. Like for instance, one thing we might want to do is that maybe we want the forward vector to be, aligned with the up vector of the camera, for instance. Like there's a lot of stuff we can do here to improve this, right? Can you show the code again? If your turret keeps teleporting, you might have colliders on your turret, because then the ray is going to hit the turret itself and it's going to like go close to the camera and then it's going to jump forward again and then go close to the camera and then jump forward. So be sure to remove colliders. No, you don't have to turn in any of the assignments. They are all optional, and so you don't have to do any of them. You can just be lazy and do literally nothing. But if you want to learn, then the assignments are designed for you to learn, right? As I would encourage you to do it because it's useful to know these things. So yeah, and feel free to like do things together with other people. Just make sure that you are kind of on the same level so that you're not... Don't team up with someone who just knows the answer because then you're not going to learn anything. Team up with someone who's about on the same level as you so then you can try to figure things out together. So feel free to do that, like whatever format you think you will learn best in. And copying from someone who's already solved the problem will not make you learn anything. Just things to consider. What do I do if I get completely stuck tomorrow? Then it's over. You're fucked. But yeah, talk to classmates. Try to figure things out step by step. It's always good to talk to everyone and share information and learn together. That's kind of something you should do in school, you know? Okay. All right. Do I come up with assignments after the stream or do I try to do it live for... I only have like 15 minutes. Ah, jeez. The turret was going to be the assignment, and so now I need to do something else. Oh god. I can feel the pressure. Usually the turret is my canned example that I pop open. Portal gun? No. Maybe make a person standing upright who tries to face away from a specific object. That could work, yeah. Um, well, there are two assignments I want to do. One should be related to matrices and space transformation, and the other one should be related to yeah, I think we can just make a more advanced turret. Yeah, I think that's what we're gonna do. And so yeah, I think I'll do this off stream. And so I will give you the assignment as soon as I figured out a good assignment. I don't want to like do this live. And let's see. Yeah, I'll just do the assignments offline, and I will send it to you as soon as they're ready. Oh, and I guess if you're on YouTube, then the assignments will be in the comments whenever they are done. And so, you know, I won't be sending them to you privately because I don't know you if you are on YouTube. So, you know. Isn't it already facing away? Not really. Technically, I have a bit of a subpar solution here, right? Like if you look at this, you can see that it's kind of rotating to the side. Generally, you don't want that to happen. And so it's kind of an incomplete solution. And so if you want a proper solution, there's more work to be done and other things to use the cross product with. And so I think maybe the first part of the assignment could be to recreate this turret and then do a few things to fix it up. I think we can also do some matrix related stuff related to this turret, like getting local positions of it, like deciding the projectile spawn locations using local offsets and matrices. I think that would be a good one. Yeah, and so I think something like that will be the assignment. But again, I will send it to you students later. If you are on YouTube watching this after the fact, it's going to be in the comments. And so, yeah, I think that's all we have time for, basically. I guess we have 10 more minutes. I don't know what to do during these 10 minutes now. I thought we had less time left. Okay, are there any questions about anything we talked about today? Elevator music? You know, I wish, but I would get a copyright strike. That's why I usually don't stream on YouTube, because YouTube is vicious with copyright strikes and Twitch is not. And so, but I don't do music during my lectures, so that's why I'm here. Backflips? I don't know how to do backflips, I'm sorry. Thank you, Freya. Amazing lecture. No, thank you. I'm glad you appreciate my scribbles. Did you write out the actual formula for the cross product? Yes. Here's the formula. The top one is the x component, so it's x, y, z. So I'm writing this in the column matrix format. How different is using the matrix functions compared to, for example, just changing an object's transformed opposition or rotation? I mean, they're used for different purposes, right? And so I don't really know how to compare them. Like, if you already have a transform that you want to move, then you should set transformed opposition and rotation and whatnot, right? But if you don't have a game object and you don't have a transform, but you want a coordinate system somewhere in space, you would use the matrix type instead, right? So they have different use cases. Unrelated question, but will you visit us on site Stockholm during any of these days? I usually don't plan for visits, but with the previous class, we've gone for lunch a few times. And I mean, I live in Stockholm, so it's very easy if all of you want to head out for lunch someday. You can just let me know and we can have lunch. Yeah. Rip the North. Yeah, I'm sorry. Don't go taking a train all the way down here. That would make me feel very... I would get like imposter syndrome and feel bad for not justifying a trip. So you're not missing much. All right. People are typing. I should drink water. When is next lecture? On Friday at 9. Your permits are taking so long? What kind of permits? Oh, are you like not in Stockholm or? Oh, resident permit, right. Yep. Okay. All right. International students, gotcha. Okay. All right. Well, if there are no more questions or thoughts, I could turn to YouTube chat, see if they have any thoughts or questions before I leave. Yeah, and then I'm gonna enjoy my post-lecture headache that I get every time, which kind of sucks. I don't know why. I always get a headache afterwards. I think it's because I'm talking so much. I almost never talk unless I'm doing these like very long streams where I like talk constantly. Okay. All right. When can we expect to have the assignments ready? At the very least, tomorrow morning. Maybe tonight, depending on factors. I might be very tired because I was very sleep deprived this morning, so I might have to take a nap. I might get a very strong headache that I sometimes get after lectures. And so it might happen tonight, but I will try to get it done tonight. But at the very least, it should be available tomorrow morning. Because tomorrow is a dedicated day to work on the assignments. And you're also free to work on the previous assignments, even though you've seen the answers already. Maybe you forgot the answers, and then you can do them again and try to figure it out. Because again, it's just for learning and getting used to using these things, right? Important questions. Will we have cat ears bonus assignment again this time? Yes, I can try to figure out an advanced assignment for the cat ears. True, that is an important question. It's a good motivator. Good. I'm glad it works. It's actually better than for the previous students. I usually use the my Twitch channel points to redeem the cat ears, and the students can only do it if they've been watching the channel for long enough. So usually it happened like at the end of the streams, but this is a good motivator. It gets you wanting to solve the problems, you know? Like we say, it's a use case. It actually leads to an important result, an important desired result. That's why we solve problems, right? Okay. All right. Any last questions before I escape to YouTube and then escape into not streaming? Sleep well? Yeah. I'll try to not nap today. I need to get my sleeping schedule in order. Okay, cool. Yeah, thank you all. Thank you all so much. I hope this was educational and you learned something today. Yeah, I think that's it. Thanks for joining. No more crucial information. Feel free to tune out and leave. And yeah, I'll stick around for a little bit if you have any like remaining questions, and I'm gonna read YouTube chat for a bit. Otherwise, the next lecture is gonna be Friday at 9. Between, you're gonna have an assignment. I'll get you the assignment at the very latest tomorrow at lunch. I should definitely have it ready. Ideally, I would have it ready in a few hours, but depending on what happens and how garbage I feel, I might not get it ready in time. But it will be available for tomorrow to work on, which is the important part. But yeah, thank you all so much for joining, and we'll continue on Friday. Okay, YouTube chat. Now YouTube chat is going to start existing. Have you read a book called 3D Math Primer for Graphics and Game Development? I don't think so. No, I don't have. The thing is, I don't read books. Like, there's a lot of people who ask about books, but I just don't read books for anything that I learn. And so I'm sorry. I don't have any. I don't have any advice. In terms of reading. Will you rename this to part 2? No, this is part 3, and then the previous one is gonna be part 2, right? I think I named the previous one part 2. Maybe I didn't? Maybe I called it part 1. Okay, I'll have to fix that. Oh yeah, it's called like part 1 assignments, solutions, or something. I'll fix the titles. It's fine. Oh yeah, so in terms of assignments, I'm not going to grade them. I think you might get separate assignments from Christer, but I'm not the one responsible for that. And so I actually just don't know what the plan is there. So I think Christer is going to do your assignments. Okay. Do you have any book recommendations? No. All right. Excuse me. Guessing there's no more questions from YouTube chat. Oh, someone asked how to join the class. You have to like apply to FutureGames, which is like a 2-year education. So it's not just a one-off class that you can kind of join easily or long term, or short term. It's a long term thing. When will the shader course be? I forget. I think it's in my calendar somewhere. It's not too far off. I think it's in a few weeks. I don't think I even marked it in my calendar, but it's at some point it will happen. Have you thought about the video production value maxing out more? If you had a big Photoshop notes down for these lectures and whatnot, that'd be a pretty good reference. I don't know what you mean by maxing out more, as opposed to what? Wait, 2 weeks on math and then shaders? I don't think I have... Hold on, I need to check my DMs now. No, the shader course is in December. Yeah, you have shaders on the 12th of December. Yeah, that's your shader course, according to my calendar and what Krister told me. I believe... Oh, data structures and algorithms is next. Right, okay. Okay, cool. Yeah, I'm gonna do your shader course. We're gonna learn how to do pixels and vertices. Yes, I'm gonna do your shader course. That's planned. So, yes. It sounds like you appreciate that fact. All right. Okay. Is that it? Any last things before I leave? Someone asked how old they are. I don't know how old you are. Okay, all right. I think that's it. Thank you all so much for joining. I hope this was useful. I hope you learned a thing or two. Sorry for not interacting with all of you on YouTube. This is, again, primarily for my students at FutureGames, and so I'm kind of not very actively reading YouTube chat. Only a little bit, but don't tell that to my students. Yeah, feel free to join my Discord server if you want. If you want to hang out with other game developers, then you can go to my Discord here. If you want to support me financially for doing the things that I do, doing like public education stuff and like educational videos and that kind of stuff, feel free to support me on Patreon. You might also, if you support me on Patreon, you're going to be in the credits of my next video on splines, which is almost done. I've been working on the splines video for about a year now. So I hope you will like it. It's been an extremely long journey just to get this one video done. But yeah, if you want to support my extremely long videos, feel free to go to Patreon. It is like my most, half of my income is from Patreon. So a lot of you guys are supporting me, which I very much appreciate. All right. Otherwise, thank you all for joining. I don't think I have anything else I want to plug, because it's hard, because I don't have my buttons that I have on Twitch. But thank you all for joining. and I will see you all next time. Oh, next stream like this is going to be on Friday, 9 a.m. CEST. If you want to join for that, I'm going to put up a thing on YouTube as well if you want to notification enable that stream. So, all right, thanks for joining, and I will see you all next time.